Alrighty. Okay. So this is Chemistry 151. We are fixing to start on the actual chapter. Last time we did just the syllabus. Please make sure you read the syllabus, check the schedule, make sure you know when things are due. Due dates are on Moodle, of course. Now, we're going to start with chapter 1, which matter and measurement. And the first part, we're going to have definitions, which are going to be in your textbook and in the PowerPoints that we're about to do. And then we get into dimensional analysis. Now, let me tell you, it's dimensional analysis is the key #1 skill for getting through Chemistry 151. And dimensional analysis just refers to, setting up problems and then putting them in your calculator. That's what it comes down to. And almost all of the problems that you see in 151 that involve math, when you get down to it, they're really just dimensional analysis problems that have special names for special things. But at the end of the day, mathematically, they're all the same. So we're going to start with definitions and such, and I'm going to go ahead and open up the PowerPoint presentation. And what I'm going to do is I'm going to talk over the PowerPoints, and I'm going to make notes on the PowerPoints as we go through, okay? And that'll save us some time. And since we're recording this, if you miss something, you can always go back and look at it with the recording. That's the beauty of doing WebEx and recording, is that we can do that. So let me go ahead and find PowerPoint here. And there it is. We're going to go ahead and start from the beginning. And so the first thing is what's the point of all of this? Is that we're studying chemistry. And chemists, we're interested in things that happen to stuff, otherwise known as matter. Okay. Our physicist friends tell us that we're applied physics is what we are. We're interested in what do atoms and molecules do, and what can we do with them? Okay, now matter is anything that has mass. And it doesn't have to actually take up space to be matter. As long as it has mass, it's matter. And for our purposes, the kinds of matter that we worry about are atoms and molecules. Atoms and molecules. And atoms come together to make molecules, and then we have these things called compounds. And we're going to work a lot with that this semester. And so every element, now what's an element? Atoms are the individual thing. An element is a handful of all the atoms. Now, where do we find elements? All the elements are on the periodic table. That's where we find them. If you look on the periodic table, there's all the elements. Now, there's only 91 naturally occurring elements. And out of that, not a whole lot of them are terribly important for us at the time. Okay, and when we take two or more elements and put them together, we end up with a compound. Now, there are just 3 states of matter. You have solids, you have liquids, and you have gases. 3 states. Okay, and I know some of you might be thinking, well, what about plasma? I've heard plasma is a 4th state of matter. Well, plasma is a gas. It's an ionized gas, which means that electrons have been knocked off, electrons have been added, but plasma is an ionized kind of gas. Depending on who you talk to, a gas is a gas is a gas. And sometimes, and if you talk to others who are into physics, they'll tell you plasma is not quite a gas. It's a special kind of gas. So, but we have solids, liquids, and gases. That's what we have for the states of matter. All right. Now, we have to be able to classify matter. All matter, we start with that. Now, the first question we have to ask, is it uniform throughout? Now, what does that mean? What it means is, and I'm going to draw on here now. I told you I draw on these PowerPoints. Let's say you have salt and sand. All right. And we have little pieces of salt and little pieces of sand. Now, is that uniform throughout? Well, it all depends. If it's uniform throughout, then it would be the same thing all the way through. Okay, and that's not the same thing. These are little salt crystals, and these are little sand crystals, and the answer is no. That would be no. Okay. Now, what would be uniform throughout? Well, let's say we have salt water. Okay. And if you look at salt water, well, it's dissolved and it's uniform throughout, but it's not the same stuff, but it is uniform throughout. Okay. Now, if the answer is no, it's called a heterogeneous mixture. That's your salt and sand. Now, many times we can tell because usually sometimes we can see it. All right, if you look real close to a salt sand mixture, you probably will be able to pick out the salt crystals and the sand crystals. If you look at something like iron filings mixed in sand, well, you certainly could see the chunks of iron mixed in with the sand. Also, heterogeneous, hetero means different. All right. And so anytime you see something where it's different anywhere around it, then that's automatically heterogeneous. Like, for instance, soil. If you go outside and you pick up a chunk of soil, different parts of that soil are going to be a little bit different. Okay. Now, the next thing we have to ask yourself, if it is uniform throughout, then it is homogeneous, which means same. This just means it's the same. All right. Now, we can't just stop there and just say it's homogeneous. We have to look if it's the same all the way through, but does it have variable composition? And what that means is if it has variable composition, that means that it has more than one thing, more than one component. You see, that's the case right here with, say, salt water. That's also the case with, say, air. The very air that you're breathing, air is actually a pretty good example. The very air that you're breathing is a homogeneous mixture. It is a mixture of 70% nitrogen. I think it's what, 28% oxygen, and a bit of argon, a bit of CO2, a bit of water vapor. But it's the air on one side of my office versus the air on the other side of my office is the same, so that makes it homogeneous. Salt water is the same throughout. That makes it homogeneous. Now, when we don't have variable composition, that means we have only one substance when we call it a pure substance. Now, if it's pure, that means we could have molecules or atoms, okay? And so these would be molecules or compounds, okay? Now remember, to be a pure substance, there can only be one component, only one. Now here's the important thing right here about elements, and this is important to make a note of this. Cannot be separated into separated into other elements. Okay. Where do you find elements? You find them on the periodic table. That's where you find elements. If you have carbon, it's carbon. If you have oxygen, it's just oxygen. Compounds, that's sodium chloride, that's glucose, that's copper Roman numeral 1 sulfide. That's all these things, okay? All right, so a lot of people miss that on the elements. I don't know why, but you got to understand what makes an element is really what I have there in quotes. It cannot be separated into other elements or into simpler substances. And simpler substances mean other elements. I mean, you can take an element and separate it into, say, protons, neutrons, electrons, but then it's not the element anymore. All right, properties and changes of matter. All right, so we've got two kinds of properties in this world. We have physical properties and we have chemical properties. Now, how do you tell the difference? After you do whatever it is, it's the same after a process. Okay? So how do you determine a boiling point? Well, you put it in a beaker, and you set it on a stove, and you crank up the heat until it starts boiling, and then you measure it with a thermometer. But let's say you're trying to measure the boiling point of water, and once it starts boiling, it's still water. If you're trying to determine the boiling point of ethanol, you heat it up until it starts boiling, but once it starts boiling, it's still ethanol. You put something on a scale, it doesn't stop being what it is. Okay, so that's a physical property. Chemical properties, as it says right here, are observed when the substance change, so it's different after the process. Whatever it is that you're doing. So how do you check flammability? You set it on fire. You determine what temperature, or if it's going to burn at all. How do you do it? You pull out a lighter, you light it. If it doesn't burn, it's not flammable. If it does burn, it is flammable. Okay, but after you've checked the flammability, is it the same thing? No, it's burned. It's burned. It's different. Corrosiveness means whether it'll pit metal, and once it's pitted to metal, it's not the same thing anymore. Okay, so the substance has changed into another substance, but really when you look at it, is it the same or different after this property? How do you measure the property? What do you have to do to measure the property? Do you have to do something that is just what they call destructive testing? Okay, so that's that's the big difference between physical and chemical properties. Is it the same or is it different? So intensive, extensive, intensive. Now the way to keep this uh, straight here is intensive means it's inside. It's a property of the substance. That's where the N of intensive comes about. So so it's independent. So whatever you do to it, it's still going to have whatever it has. Okay, so density, that's grams per milliliter, no matter how much you have. A boiling point, does it matter if you have a lot of stuff boiling or a little bit of stuff boiling? Well, guess what? If you measure the temperature here, it's going to have the same boiling point. Color, does it matter if you have a bunch of it or a little bit of it? If I have like a pound of gold or I have an ounce of gold, it's still going to be golden yellow. But extensive, though, depends on how much you have. Like, for instance, mass. How much heat to heat it up? How much heat to change the temperature? Well, what would make sense? If you have less mass, it would take less energy to change the temperature. In other words, think about putting it on a stove. If you have a big pot of water versus a small pot of water, the extensive property would be on that particular stove would be how long does it take to reach to a boiling point? How long does it take to heat it up? Well, if you got a big pot of spaghetti water versus a little pot for making some tea, well, the spaghetti water is going to take a lot longer. That's an extensive property. It does matter how much you have. Now, physical changes, chemical changes is the same deal with physical chemical properties. It's the same thing. It just it depends on whether you're having a change or not. Chemical reactions. Um, we're going to get into that next chapter. Okay, don't worry about that. Separation, we're going to do a lab on this with separation. Filtration, that's when you pour it through a filter. You separate a solid from a liquid. Distillation, you're taking advantage of difference of boiling points. Things with lower boiling points come off first. Things with higher boiling points come off last. Chromatography, differences of adherence to either the solvent phase or the solid phase. Okay, we won't do any of that this semester. It's a pretty fun experiment though. All right, units of measurement. All right, here are all the different kinds of units that we have. There are many, many different kinds of units. We will use, let's see, let me check down here if we have, yeah. Okay, we're not going to use necessary. Now, there are times when we must use SI units, okay, when we're doing calculations. There are times, but many times we won't. For instance, we're going to use metric units in addition to SI units, and SI units are metric. All that means is powers of 10. All right. For mass, we often in the lab are going to use grams. And if you're out in the field, you may actually be using milligrams. And if you get really small quantities, you might use a funny looking U, which is a microgram. Length, we use meters, that's the SI unit, and you're forced to use that in certain situations. But most of the time, when we're in lab, when you're doing measurements, you're going to use either centimeters or millimeters. And if you start talking about things like wavelengths, you may end up with micro, micrometers or even nanometers, which is wavelengths of light, and so forth. Seconds, that's time. Kelvin, that's the SI unit, but we also use degrees Celsius for many measurements. Amount of substance, that's always a mole. All right, and don't worry about these guys. The ampere, that's for electronics. You do, and the candela, these are things that you would use in physics. And when you go on to take physics, you'll do labs where you do amperes and candelas and so forth. All right, we got the metric system here. I would suggest that you memorize from, here we go, from nano to kilo. Now, that's what I would suggest that you memorize, and the relationship between those, okay? And I'm going to show you how to go back and forth when we get into dimensional analysis. I'm going to show you how to go back and forth between different prefixes. It's important to be able to do that, but try to memorize. You can memorize the entire list, and good for you if you do. But you really should go from kilo to nano as a start. Those are your most practical daily sort of prefixes that you're going to run across. This one is fairly rare. If you're in the medical field, you might talk about so many milligrams per deciliter, because that's how nurses and doctors, they talk about test results. This is in terms of deciliters instead of milliliters or kiloliters or whatever. Okay, so memorize those. That's fine. Whoops, went a little too far here. And volume, let's see, it should have been back here. They didn't put a volume in there. Volume is a derived unit anyway. And so usually we use a milliliter. A milliliter is 1 centimeter by 1 centimeter by 1 centimeter. And by the way, a milliliter, that's an M, a milliliter is exactly equal to a cubic centimeter, and that's also known as, you may have heard this before, a cc. Particularly if you're in the medical field, we'll have say, give me so many cc's or whatever. What they mean is so many milliliters or so many cubic centimeters. It means exactly the same thing. Cc and centimeters cubed are exactly the same thing. Now, temperature is, by definition, it's how hot and how cold things are, but it's a measure of the average kinetic energy of the particles. What do we mean? Well, if you get down to the atomic level, well, here's some atoms that are next to each other in a solid. Common picture that you may have seen in high school or in some other science picture, this is a solid, by the way, is that these solids, these particles are fixed and they're not moving around, but actually they are. These represent average positions, and these guys are constantly moving randomly, constantly in different directions, okay? And when they move, there's kinetic energy associated with that motion, because you know that energy is 1/2 mass times velocity squared. And so the higher the velocity, it goes to square the velocity, the more energy you have in these particles to get them moving. And so the faster these particles are moving, the higher the kinetic energy, and by definition, the higher the temperature. And as you cool things down, these guys get slower and slower. Okay, so these positions represent average positions, but they generally stick around on the same spot. Okay, now if you heat them up high enough, they break their local attractions and they can start moving around and become liquids and eventually become gases, okay? And the relationship is on these three scales over here between the Kelvin scale, Celsius scale, and Fahrenheit scale. And there's conversions to go back and forth between these. Now, most of the time, we're going to measure things in Celsius. Kelvin scale, sometimes we're forced to use Kelvin. Actually, many calculations, you have to use Kelvin. But you measure in Celsius, and to go from over here, you say degrees Celsius plus 273.1. Is it 15? I think it is. Either 15 or 1. Yeah, it is 15. 273.15. So you just add 273.15 to the degrees Celsius, and that'll give you Kelvin. All right. So, whoops. All right. And so Celsius we use a lot, and it's defined in terms of the boiling point of water. So we have boiling point of water up here. We have the freezing point. Same thing with Fahrenheit scale. It's defined in terms of water, and that's fine. But the only problem is that you end up with negative numbers. And so, since Kelvin is defined on the properties of gases, we end up with this conversion factor, which I just showed you. But this is the really important thing right here. No negative numbers in Kelvin. And you may say to yourself, well, why does that matter? Well, I can give you the volume of a gas is some constant, doesn't matter what that constant is, times the temperature. And as long as the temperature is positive and K is positive, then the volume's going to be positive. But what happens if you get a negative temperature? If you plug in a negative temperature for the temperature, well, guess what happens? If that constant is positive, now you have a negative volume, and that's a real problem because there's no such thing as negative volumes. Okay, you can only have positive volumes. And so by setting our temperature scale in Kelvin so that you don't have any negative temperatures, in other words, when we hit 0 Kelvin, that's as low as you can get, you don't end up with negative volumes, which would be an unreal situation. Okay. And so we have some conversion factors. You can do this on your own with the conversions. Generally speaking, we don't usually measure things in Fahrenheit, so the only conversion we ever really worry about is going from degrees Celsius to Kelvin. All right, derived units just means you have more than one property. That's density, it's mass over volume. I would highly suggest not looking at this as something to be solved. In other words, it is true density times volume is mass. This is true, but I would suggest not doing that way. What we're going to do is, let's see, I would say not recommended, but you can. It is true. Density times volume is the mass. But what I would recommend is we're going to use these things as conversion factors, okay? We're going to treat density as a conversion. All right, now we're almost done with the PowerPoint stuff, so bear with me here. So uncertainty. Every measurement is uncertain. And I'll tell you that I'll just put this up here. I don't remember if it was on the slide, but the last number in any measurement is always estimated. Always. Which means you have to read between the lines. In all measurements. Lab 1, when we do the measurements lab, we're going to be measuring in between the lines, and I can tell you a burette goes out 2 decimals, and graduated cylinders usually go out 1 decimal. Okay, so which one is more accurate? The one that goes out 2 decimals. Okay. Accuracy is a lot of times it's a determination of reproducibility is accuracy, but it's also a measure of how many decimal places can you go out. So a burette at 2 decimals is more accurate, more precise than say a graduated cylinder, which goes out in 1 decimal. And like I said, we'll do that in lab number 1. All right, significant figures. Do I want to go through that? Let's see, SI. All right, all non-zeros. Let me stop the PowerPoint presentation here, and I want to discard that. All right, and let's go back to this guy, because I think I'm at the point where I would like to just show you here. Let's see. So, sig figs. All right, I promise you, I mean, sometimes I do PowerPoints, but I don't always do PowerPoints. All right, actually, it's fairly rare for me. All right, significant figures. Okay, so you're going to see, you know, if you talk to the physics guys, they'll tell you one thing us chemistry, Gen Chem 1 people do is by the time you get out of Gen Chem 1, you have got, if you don't know anything, you'll know significant figures well. Significant figures comes with a lot of practice. Let me make sure nobody's trying to get in. Nope. Okay. And significant figures is so that you can correct. It is the purpose of significant figures is to correct calculator answers. That's the purpose of significant figures, is to correct calculator answers. Okay. Now, you may say to yourself, well, why does that matter? Well, if you have a certain amount of information, let's say you have 1.2 centimeters, and you multiply it times, let's say, 3.9 centimeters, and you get an answer. I'm going to just show you an example here, and I pull out my calculator, and you go 1.2 times 3.9, and you get 4.68. This is your calculator answer, right? And sometimes, you know, you can do a calculation. I'm getting a lot of beeping over here. Hold on just a second. I'm going to take a look here for just a second, just see what's going on. All right, I'm getting some beeping. Let's see, meeting's open, still open. Okay, all right, I'm gonna go back to sharing. I just keep hearing a beeping in my headphones. All right, so I'm gonna go back to sharing here. All righty. So, all right, so you get this, and this is a calculator answer, 4.68 centimeters squared. Okay. And, you know, when I was in your position, calculators had just been invented, believe it or not. And they were a wonderful thing, because if you've ever had to do long multiplication and long division, you know, it takes up time. Okay. And that was a great thing. And my professor, he was like going, well, you can't just write down every single digit. You have to go by something called significant figures. And I'm like, what do you mean? You know, what the calculator, it gave me an answer. It gave me a great answer. It's an answer faster and more accurate than I will ever do. And the thing about it is it's like this. It all comes down to information, okay? You can't just add more information than you have. In other words, the only information I have here for the first one is I have 2 digits of information over here. And with my ruler, the best I could do was out to 1 decimal place, but I got 2 digits of information there. But now you're going to tell me that I can have 2 more decimals over here. And that's just not physically real. Trust me, you just can't just add extra information. Now, it makes sense, though, that with my answer that it would have, you know, at least out here, you know, because I can go out, the best I can do with my measurement is go out 1 decimal place. At least my answer ought to have at least 1 decimal place in there. So the first rule of significant figures is before we even put in the numbers in our calculator, we get an answer, we have to decide what's significant over here with the numbers that we're putting in. So rule number 1, if you measure it, if it's measured, it's significant. Okay? No matter what it is. If you step on a scale, like I stepped on a scale this morning, all right? Here's my scale. And you get a measurement, 168.4 pounds. Okay? Then this has 4 significant figures because the scale has measured all 4 digits. And if I step on it tomorrow, and God willing, I will have lost a little bit more weight, and it's 168.0 pounds, well, it's still 4 significant figures because this scale is measuring out to that first decimal place, and I'm getting 4 digits out of it. I'm getting 4 digits. All right. And so whatever you get, whatever you measure, no matter what it is, if you can measure it, it's significant. Now, the problem is with placeholders and defined. What does that mean? Well, let's say you have a very large number. Okay, let's say you have a very large number, and it turns out that with whatever which device that you used, the best you could do, these were measured. These were measured, and these were just placeholders, and you know that. All right. Placeholders tell you how big or how small something is. And instruments, whatever you're measuring with, can only measure but so many so many digits of precision. They can only measure but so much. Okay. And so depending on device, if you pay lots and lots of money for something, you can go out a little bit further, but there's not an infinite number of digits that you can measure with any measurement. Okay. And so those are placeholders. So I didn't measure the placeholders. These were not measured. Placeholders are not measured. They just tell you how big it is. Now, what's the rule? If it's measured, that's significant, right? And if you don't measure it, well, then it's not part of the significance of the number. Okay, it's not part of it. It's just a placeholder. So by that logic, we would say this was 1, 2, 3 digits, and these don't count, and so this should be 3 significant figures. And similarly, if you take a look at say a very small number, let's say we have this small number right here. Well, similarly, these are just telling you how small. These are placeholders. All right, they're not measured. You don't measure the placeholders. They just tell you it's a small number. Okay, that's what they're telling you. And so they're not measured. If they're not measured, then all these zeros up here must not count for significant figures either. If you don't measure it, they don't count. So what do? Well, the only ones that we measured were these guys over here, 1, 2, 3, 4, and so we say this is 4 significant figures. Okay, so but we've got to be able to look at a number. Now here's the skill, and this is where Sig Figs comes in. We got to be able to look at a number and decide how many significant figures it has. Okay, so the first rule is if it's measured, it's significant. Even if you end up with zeros like over here on the scale, if you measured the zero, it's significant. Now the problem comes in with if you don't know anything else, but you do have zeros, we got to have some rules. Okay, so how can you tell? So the issue becomes determining whether zeros are significant or not. So significant or not significant zeros. Okay. Now, there's really only two rules. We can make up all sorts of other rules, but there's really only two rules. And that is, we have these things called leading zeros and trailing zeros. Leading zeros. And they look like this. They're in small numbers, and then we go 0. I might as well put a couple zeros out here too. Why not? 0, 0, 4, 3, 8, 1. Okay. And leading zeros means that they're out front and they're the only ones out front. These are all leading. Okay. And the rule is going to be are never significant. Okay, that's going to be our rule. Okay, leading zeros are never, ever, ever significant. And it doesn't matter if there's a decimal in there. It doesn't matter if there's no decimal. But if it's all zeros leading out to the left, just the zeros, then they're never significant. So in this case, we would these zeros over here, this is the rule. So we know that these zeros over here are not significant. None of them are. And the only significant numbers, just by looking at it, now understand, we're trying to decide whether a number is significant, whether zeros are significant or not. We're going to assume that if we got digits like 4, 3, 8, and 1, that those are automatically significant. So it's zeros that we have to make a decision. And so we would say, well, that's 1, 2, 3, 4, and therefore that has 4SF. Okay. Now, trailing zeros is the other situation. So we got two situations. We got trailing zeros and leading zeros. So trailing is for big numbers. And so we look at it and we go, all right, well, let's write out an example here. And we go, we got 140,000. Now, trailing is these guys going out this way. And they're only zeros. And that's all you have is just zeros. But the rule is a little bit different for trailing zeros, just a little. And what we're going to say is, we're going to say that they are not significant unless there's a decimal. Somewhere. And when I say somewhere, I mean anywhere. Okay. Now we look at this and I see no decimal. So this one is no decimal anywhere to be found. And so therefore, this has 1, 2, 2SF. Okay. So that has 2SF. So those zeros are placeholders. And we're saying that just because we're going to say that if we're just looking at it, we're going to say that that is what we're doing. Okay, so let me go ahead and move this up just a little bit. Okay, so let's try another one. And so how about if we combine the two things? Well, let's do another one. Let's just do one more with like the trailing. But how about if we take that same number, but we put a decimal in there? Okay, so these guys are still trailing, but what do we have over here? There's a decimal. There's a decimal there. And so in that case, all the zeros count. So everything counts. They're not significant unless there's a decimal somewhere. And by the way, and it does not matter where that decimal is. I deliberately put them in between those second two zeros to just show you that it truly does not matter. And so we go 1, 2, 3, 4, 5, 6, and therefore this is 6 significant figures. Okay, I only do one more example. Let's try to mix it up a little bit. All right, so how many sig figs do we have here? Well, we look at this and we see, first off, these are leading. These are trailing. And we look at this and we say, well, leading's never significant, so those don't count for anything. Trailing, on the other hand, we have a decimal there. And so therefore, we count those trailing zeros because there's a decimal somewhere, and it doesn't matter where the decimal is. And so we go 1, 2, 3, 4, 5. 5SF. Okay, 5SF. And so, like I said, now, if you're measuring it, you would automatically, whatever you got off the measurement would be automatically measured. So you would know that if you measured these last zeros. Now, how do you tell? Let's say, for instance, that you had a device, like for instance a scale, and you did get 1400. But this is all, but you know it's all measured. You know it's all measured. So what do you do now? Well, if you know all of them are measured, one signal that we can do is you add a decimal. If you have a decimal, what's true? All the zeros are significant. And why is that? Well, if you add that zero in, what do you have here? You have trailing with a decimal. And so we would know that would be one signal to tell us that we have 4 significant figures. That's one way. Another way of telling whether you have significant figures to report your answer out is use scientific notation. And so scientific notation, let's put that in scientific notation. It would be what? 1.400 times 10 to the third. And what do we see here? This, even if we had no decimal there, would be ambiguous. But what do we have here? All scientific notation has a decimal in it. So if you have zeros, that would be 4SF. And if you knew, for instance, if you knew, for instance, for sure that that is placeholder, and that zero was measured, let's say hypothetically, then we would, there's no good way of writing it in any other way other than scientific notation. In that case, you would say 4.0 times 10 to the third. So now you have 1 0 in there, and that would be 3SF. So if there's an ambiguity of trying to indicate which digits are significant, which zeros are significant, and which ones aren't, what you do is you just go ahead and just put it in scientific notation is what you do. Okay, you just put it in scientific notation. Okay, now where is all this leading us? Well, when we do calculations, we have to use what's called rules of significant figures. And what we have to do is, so that we can get the correct answer, we have rules for multiplication and division. This is sig figs in math, because we have to know where to round our calculator answer, because all this was getting to the same place, which is you plug some numbers in the calculator and you got to know. And I think we already did the multiplication, but just to remind you, and we're going to get plenty of practice in it, is that multiplication, you go by the least number of sig figs, and that's division too, multiplication, division. And addition, subtraction, you go by the least number of decimals, okay? And so to be able to do that, you have to be able to identify how many sig figs that you have in the things that you're working with. And really the big thing that we're trying to emphasize right here is that if you have zeros, you have to know whether they're significant or not. And so, but a lot of times with the math that we're doing, that does not become a problem. What ends up becoming a problem is you have to go through carefully through the problem and figure out what the sig figs is for everything. And finally, if it's defined or metric, then it has no sig figs. It's not zero, it just doesn't matter. And so defined would be like, say, 2.54 centimeters equals 1 inch. That's defined. It has no sig figs. Metric would be like 100 centimeters equals 1 meter. The 100 centimeters doesn't count for sig figs. What matters is generally the only things that are going to matter for sig figs is your measured numbers. And you may only have one measured number in a calculation. You may have two measured numbers and one defined, and you have to go by the least number or whatever you have. So that's what you have to do. Now look, we're going to be doing lots and lots of calculations as the semester goes along. Every calculation, whether you're doing them on your own, we're doing them in class, or we're doing them in lab, you must use sig figs. Now, remember what I said, sig figs is for the calculator answer. So you don't ever round until the very end, okay? If you have more than one step, carry extra digits. They're called guard digits. And if you don't, but if you round at every step in like a multi-step problem, you'll end up with rounding errors. They're usually not serious, but they're enough that, I get my answer and it's 4.184. You rounded twice and maybe your answer is 4.218. Okay. These are essentially the same answer, but rounding errors can creep in and they can cause real problems. So what you do is you just carry over some extra digits and do your significant figures at the very end.